understood that we don't know how to do it. And we changed the idea, changed the key technological idea from the new material itself to the coding of the material. And it automatically changed the I and the M automatically. That's why we're receiving yesterday in the bar. Surprise! So we decided to take the coating to put it on the metal so that it is seen on the in the luminescent light. So it's kind of new method of non-destructive control. Very easy new method. We decided to widen, to narrow the market. We decided to take the aerospace as there are highest safety demands and it's wide and growing market. And then we decided again to narrow and try to focus on one of the key problems in aircraft engines, like the blades. We decided to work with them on board. We decided that what we're going to do is to cover the blades with this coating and then to inspect them with a special device, immediately showing that there's crack, there's no crack, just giving the exact answer. So the outcomes are actually obvious. It really decreases time and it increases safety. During the following slides, we will again sticking to your guidelines. So 2 slides are dedicated to T, to I, to M. And first of all, we were trying to make the universe of each element. So that's like a structure of what we done. As we were starting with the market, our idea came from market. What are the needs? So this is the first element, M. The needs of aircraft manufacturers and air companies are obvious. It's to reduce the costs. It's the need of each manufacturer. Reduce the cost of inspecting, because inspection takes time. Time is a huge amount of money when the plane is idle, standing on the ground. So we reduce the time, we reduce the cost. Then safety, of course, safety, as these cracks and blades are really a significant problem. And just a couple of years ago, there was an accident with A380 new Airbus, where the blade was destroyed and the engine was destroyed either. Everyone was stayed alive. And the reliability of the data. It's not all of screening and inspecting procedures nowadays give the exact answer. When the technical guy is inspecting the part with some kind of device, he can miss the crack, and that will cause a problem. I won't be talking about all the information about on the slide. You can read it. Maybe further you can ask questions, but I'll just stick to key points. So I'll move further. This slide actually just giving some figures about what I've said just right now. So it's how much time actually they spend on inspecting, and so we can see that it really can save money. So again, some figures about the certain airplanes, some trends, and actually the result that our technology actually fits into all these trends very well. Then actually the most difficult part of this issue. Yes, it's easy to say, but not easy to do. Here is a combination of constituent-related and embedding technologies. Perhaps I won't be giving comments on related and embedding. We analyze it, we check it, we get lots of information. Maybe you can ask further. The most interesting to my mind here now is the constituent technologies. So what are we doing with this blade actually? Yeah. So we were looking for the coating that can possess such features. And actually, now in the world, there are several scientific groups spread among different universities possessing some kind of groundwork made about this technology. We analyzed these articles and we tried to use the experience, the technological experience of our guys from our group, and we are planning to use the aluminizing of the blade and then plasma electrical oxidation of this blade, so that if it cracks, because the crack on the blade comes out from the surface. That's the general process of cracking. So it's quite obvious that the coating will work in this case. So when it cracks in the luminescent light, it's immediately seen. It's immediately seen, immediately detected. Visible, yeah. And by the way, very significant thing to say that this coating is also hardening. So it's not like just something on the blade, it's hardening. So nowadays, some manufacturers already use composite ceramics for hardening the blades. It's almost the same actually, it's almost the same effect. Here's just some illustrations like on this picture, what is the coating looks like, and what the plasma electrical oxidation looks like, and actually what we're planning to use as inspecting technology to diagnose these things. So the technological benefits are, as I've said, it's hardening the coating, it's also a thermal barrier, as there was in extremely high temperature in the turbine. And so our goal is that we suppose that it is visibly can be easily diagnosed. That's about the technology. Second, next logical step is implementation. So how are we planning to combine these technologies together in order to get the required effect? So here's the method of production, and it is illustrated. Unfortunately, the quality is not really good. This thing was created by our group. It's like, I don't know how, but it actually shows what we're doing. This is the blade. This is the blade. Yeah, believe me, it's the blade. So it is inserted into the aluminum, so it's aluminized. Then it receives here the first coating, plasma electrolytic oxidation, not easy to pronounce, and then it receives the second coating, and after these two coatings are on the blade, again we suppose that it's not easy to create a system, diagnose to see these cracks. In terms of the IP, how do we see this business? Actually, all these elements separately are known in the world and are used these technologies. So we suppose that we need to make a patent on this method of coating. The method of coating we propose to keep as a know-how and patent and method of diagnosis. So we will need to say something to the world how we're doing this. We suppose that we will do it by saying how we do it. But actually, technically, how we do it within our business. So this is the first pillar. Going further about implementation, let me start with the business model. So we see it as a service company. First idea was just to give this technology to, I don't know, Rolls-Royce, let them do whatever they want, just to put it in the existing manufacturing cycle. But in this case, we lose the know-how, we lose the IP, as you said in your lectures, when you just sell the technology, it's not an innovation. So we try to think how it could exist in the form of business. So to our mind, it can exist as a service company, B2B of course. So we're inviting aircraft engine manufacturers to give us their blades. We're making some modifications, some processes with these blades, and sending them back to the manufacturer. That's actually our idea of our business model. Then the second question comes, how to monitor this? Like, okay, this blade is installed in the engine, what do we do next? So next, as we suppose, the most efficient way to inspect this kind of blade of the engine is to have a device that almost immediately is showing whether there is a crack or not. So the algorithm we propose is to do the following. When the jet is on the ground, the technical comes up to the engine and inserts a special device containing the luminescent lamp and a sensor. The turbine makes 1 or 2 test rounds, circles, and the sensor is watching whether there's in any place any red or, I don't know, other color. And it immediately is, I don't know, signals alarming. There's a red color. So it's doing it in terms of all the levels of turbines. It's okay, letting the plane go. The thing is that at present it takes efforts to uninstall the engine, to open up the hoods, and to using some difficult and taking a long time for process to inspect each blade. This technology is just doing it like 5 minutes. So what we're planning to do with these devices is to, in terms of manufacturing them, just to give an outsource to some, I don't know, Chinese company. It's not difficult to create this thing, and to certify this precision, as these operations are done by the ground services in the airports. So if the planes are equipped with these blades, automatically the ground services need to have certain equipment to maintain these engines. So we're saying that we're certifying them, and through the certification we provide these devices to ground services, I don't know, all over the world, in the airports where these airplanes fly. So that's the basic approach to the business model. We're trying to calculate costs. It's not really easy on this stage, but according to very preliminary estimations, we suppose that we can generate some margin. So again, in terms of the supply chain, what we need is the aluminum, and we look through the suppliers of aluminum. It's not a problem to get aluminum. It costs like $700 per ton. And some chemistry is also not difficult. Compounds, like it's all easily get in the market. Again, in terms of the sales channels, we think that we need to start with direct interconnection with engine manufacturers and with airports or other service companies. And in terms of the competitions, it's obvious that we are competing with companies providing other methods of non-destructive control. They are actually shown here. Yeah. So this is what are they doing now? And here's the list. Also, an important point that I didn't mention is, of course, accreditation. So we need to go through the difficult procedures anywhere we go: Russia, Europe, US. it won't be easy to prove that our technology is safe and it works. So this is also an important element. We even put it just right up, because if we don't have this, we don't have nothing. So basically, this is the picture of our idea. Now we don't know 100% whether it works or not, and we need definitely to make some lab experiments. And one colleague from our group is making very common things in terms of his work. So he's saying that is 80% can work. His personal thing. So thank you very much for your time. Me and my colleagues are ready to answer questions, give the comments, details.
Great. So,
I was just saying, he did a nice job on definitely going through the process and filling out the universes and everything. And I really like the way you get to really figure out how to do that. That's very impressive. And I think going forward now, just having to let the different things work on each other. I think, obviously you start with the cost part, and the cost part is, a little bit more complicated than just the materials cost, right? Because you're going to have the operation cost of doing the testing and all that sort of stuff. So I assume you guys know you'll have to work more on that. That's just but that's okay, because as you said, you can't know everything all at once, right? So you just move from one area of uncertainty.
Frankly speaking, we remember about the cost yesterday at 2 a.m.
Yeah. Yeah, that's okay. Yeah, because there's this just continues, until either you're successful or say not. There's always something else to reduce the uncertainty. That's good. The only other question I had was the mechanism for detecting it. I noticed you had aluminum oxide. So what is the mechanism for seeing that there's a crack there?
with the purpose.
Yeah, photoluminescence of cracks. So what's happening here?
As soon as the crack appears, this coating is also cracking immediately.
Okay.
And this coating, as there's no longer this coating upon this coating also cracking, and it is because of this oxidation, it is seen. These changes in this coating are seen in luminescent light.
So the coating itself luminesces?
Yeah.
Right.
Okay.
Aluminum 203
Yes.
has a quality of luminescence.
It has luminescence.
Yes, and our coating have its layers.
That's our chief technologist.
Yeah.
Two layers here. First of all, we do this plasma electrolytic oxidation in alkaline solution without something that contains silicon. And next stage of plasma electrolytic oxidation, we add something that contains silicon into a solution. And the second layer of our coating grows. This one, silicon O2, silicon dioxide, plus aluminum oxide. And this is the biggest part, it's the smallest part. And when this outer layer cracks like this is cracked. And we light source of light here, and our detector can detect the luminescence of aluminum 2 of the. When aluminum 2 already coated by second layer, we are unable to detect luminescence.
Okay. And obviously, there's details like are you scanning the laser beam, or like how you do the photoluminescence? Are you taking an image, or
Yeah.
how does that work? Those are all details that have to be worked out, right?
So I think that you did a great job applying the model. You narrowed it down relatively early because actually this is a question. at this point, well, you want to really keep your market into universe, more open. But like this is sort of with any of the possibilities, and you kind of like the first one you started to iterate already, like you go like, oh, we don't really know how to do this, and so on, So in a way, like you address all the points that you need to address for every sort of possibility, There are a couple of things, just sort of, I'm not an expert in this, but there's a couple of things in my mind, that on this particular thing that you chose, is that there is, I think, a little bit of a technical difficulty here, okay? Because when we're talking about the turbine blades, we're talking about, I think, 1600 degrees Celsius, okay? And there's like nearly no, like very few, we're not talking about the fan blades here, right? The one that you see. We're talking about the ones in the engine, the turbine blades, right?
High temperature.
Yeah, I think it's like 1600 degrees or something like that.
And more.
It's always more, right? So the problem is, like the reason why, and I think these turbine blades cost like $10,000 a piece, right? So as far as I'm aware, they even have to have a specific surface structure, because there is basically no material that could actually withstand that temperature, okay?
Yeah.
So you have to actively have a flow, like a fluid dynamic sort of cooling of the surface. So what I'm thinking is like a titanium, very special titanium alloy, I think. It has to be nickel, yeah. But it has to be perfect single crystal to work, right? Like it has to be
so it's new modern technology for compressor blades.
Right.
For turbine blades, they used cost die of high temperature alloys.
Yeah.
Nickel, titanium, chromium.
Right.
And we have to here the feature of